Yep.
Okay. For our last talk of the day, we have Krishna from UC Davis and Hong Kong here to tell us about drifting models.
All right. Thanks for the invitation and for organizing this wonderful workshop. And also, the last speaker provided a little bit of a segue to this drifting models. So I'm going to be talking about some theoretical results on this drifting models. Although the title of this workshop is like Diffusion Generative Models, I think the generative part kind of also captures drifting in some sense, right? All right, so here's the outline for this talk. So I'm not sure if everybody in the audience has seen drifting models or know the intricacies of that a priori. So I'm just going to spend some time introducing drifting model from scratch a little bit, and then discuss about like two types of finite particle rates for drifting models, one with a conservative velocity field and the other with a non-conservative velocity field. So the non-conservative velocity field is what was proposed in the original paper by Deng et al. And others in Kiaming-Hayes group. But many people, including Valentin and Arthur Gretton, have advocated for conservative velocity fields, which has this nice connection to Wasserstein gradient flows and things like that. So it really can help us understand what's going on there. All right, so this is a very compressed introduction to how I think of, or many people think of, like mostly flow matching samplers, but also diffusion samplers. So you have your x naught or psi to be your noise, not necessarily Gaussian, but just Gaussian for simplicity. And then you have your x1 to be your data nu that you wish to sample from. And in flow matching or probability flow ODE and things like that in particular, you would like to learn a velocity field, which we call here by v theta. So it is both indexed by space and time. So you're essentially learning a time varying velocity field whose such that at the endpoint 1, you're going to get your data from the target distribution that you wish to sample from, right? So, and then sampling, or in machine learning language, inference, kind of corresponds to just discretizing this ODE. So you're going to do something like this type of a step-by-step update, where you're required to evaluate the velocity field for how many ever number of times you have to get epsilon close to the target in some sense, right? So the term neural function evaluations, this was used in a couple of talks in the morning. So so if you want to, so for example, in the talk in the morning for high accuracy sampling, so you will have to run for at least log of 1 over epsilon times to get epsilon close to the sample, and then there's like dimension and everything like that, right? So intuitively speaking, or visually speaking, so you have the noise and then like the same velocity field which you're evaluating at time 1, time 2, so on and so forth. And then like each time you have to call this neural network, and then you do a pass through the neural network, and then finally you get somewhere closer to the data, right? So the point or the problem that drifting is trying to address is like, can you get away with this whole iterative sampling type of method and then just do this type of generative modeling with a one-step process in some sense, right? So basically, your given data, or I mean the noise, let's say here the psi, and then your goal is basically to learn a single mapping G indexed by data. Typically, it's a neural network in the literature, such that like it gives you already a random variable x, which is following your target, right? So here your NFV is essentially 1, essentially, right? So basically, you're just doing one evaluation through the neural network. So the goal here has been essentially to get like multi-step sample quality, where sample quality is like a subjective thing, or one can argue about it. Like FID is like one thing which people try to use, and then like there are other versions of that. But can you get the same sample quality, or maybe perhaps better sample quality with just at this one step NFV or 1 NFV. And there are some reasons to do that. Basically, you don't have to do some sequential ODE solving and things like that. And then like you can just do one batch forward pass for generating multiple samples and things like that. And so the reason why this drifting methodology got popular is, as was also alluded to in the last talk, on ImageNet, they were able to report like same or improved FID scores in comparison to like the state-of-the-art diffusion models and other types of generative modeling techniques at this one-step cost, right? So that got people interested in drifting. So before going into the drifting idea itself, so this kind of like I'll talk about this a little bit more in the rest of the talk, but so it's kind of using, but before we proceed, let me just first tell you that drifting will be a deterministic interacting particle system at the end of the day, right? And diffusion model is basically a stochastic sequential system in some sense, or MCMC type of system, right? So this type of dichotomy between like deterministic interacting particle system and iterative stochastic system kind of already happened like a decade ago in the sampling world when Chiang, who's probably going to be there soon in this workshop, so his group proposed like something called a Stein variational gradient descent, which is a deterministic interacting particle system for sampling, right? And the analog in the stochastic world to that is like Langevin Monte Carlo, or like proximal samplers and things like that, which also have the same Wasserstein gradient flow interpretation, right? So do you want to do like a deterministic interacting particle system or a stochastic algorithm like Langevin diffusion or something, which works well in practice, which works well in theory, and so on and so forth? This whole game kind of started being played even like a decade ago in the sampling world. And in a way, it is kind of like a deja vu now in the generative modeling world that like, again, there's this diffusion model, and then like now there's this drifting model which has been proposed. Like one is a deterministic interacting particle system, and then the other is a stochastic MCMC type sampling system. And so there's always this debate of which one to use and which one to not use and things like that. But even in the sampling world, the story is not settled, and in the generative modeling world, I assume it will take some time to settle the story here, right? But coming back to this drifting basic idea is the following. So you have the central object in this drifting world is a velocity field V that takes in that has access to your data distribution and your current training step. So your theta is going to be the parameter of your neural network at a current training step, and mu theta is going to be the push forward of the base distribution, or the input distribution psi, with the current parameter theta of the neural network, right? So the velocity field is going to compare these two distributions, and then there's going to be based on a kernel and KDE and things like that. So the h is the bandwidth of the KDE or the kernel and things like that, right? So how do you define the velocity field is something which we will look at in the next several slides. But given such a velocity field, what you do is like you update your current particles in an interacting way through this update return right here, right? And there is no additional randomness or anything added to the system, so this is why it is a deterministic interacting particle system, right? And what you do is like once you have this new updated particle x tilde, you try to model you try to regress your g theta of psi, which is your neural network, evaluated on the noise. You basically take that and regress against the new updated particles xi tilde, right? So, and then you try to learn the parameters of this neural network on the updated particles, right? So pictorially, you have the following visualization. So essentially, at iteration 0, you initialize at random your theta naught, and then you do a g theta naught, and then you get an x naught of the psi. So the blue points here are basically like the current target particles, and then the red points here is the intended target that you wish to have, right? So your velocity field is going to compare these two things, based on which you're going to update your theta naught to some theta 1, right? So once you get your theta 1, you're going to do again g theta 1 of the psi. So and then your particle, the current particles are hopefully going to get closer looking to the target that you wish to sample from. And then you keep, you use the same velocity field to compare this blue particles and red particles at iteration 1. And then you get the updated neural network parameter theta 2, and then you keep repeating this and so on and so forth, hoping that at some point you get the true target particle that you wish to sample from.
Sorry, where is the interaction coming from here? Can you go to the previous slide?
Yeah.
This equation x tilde is x and a plus eta v. Is there interaction there? There's no interaction.
Yeah, so basically the way this mu theta is going to be defined is going to be based on a KDE, and that will bring in the interaction. So that it's going to come in the next slide, right? So
at the level of evaluating the loss, there is no interaction.
No, the training part is like, yeah, there's no interaction at the training part. Yeah. So essentially, so now, yeah, so this is the same description given in equation, basically the same as the previous slide given in equation. So your g theta k of psi k is denoted by xi k for I going from 1 to n. And then based on which you're going to have the new updated particles xi tilde of k. And then you have this loss function where you define the stop gradient version of this, so that like you do not update, you do not take the derivative with respect to the theta when you're evaluating this guy here. So first thing, important thing to note here is this will also have a theta, so you just don't do the derivative with respect to that here. So right, so essentially just to reemphasize the same thing, in the learning process of the so in the training process of the theta, the neural network here, so you have the psi, you have the xi k, which is like passing the psi i's through the neural network g theta. So you have this velocity field based on which you update and get the new particles xi tilde k. You have the stop gradient based regression here, based on which you're going to learn the parameter theta, and then you pass it through this, you just repeat the same process over and over again, right? So let's define where we are going to get the interacting particle system from. Once again, I wish to emphasize that like in the previous slides, for example here, I'm indexing the velocity field with the true current density of the particles. Right? So in reality, you will not have the true current density. So what you do is like you will do a KDE to estimate the true current density, and that's where the interaction is going to come from. So basically, when we are talking about the particle version, I'm going to be indexing the velocity field with the xk just to denote that you are going to be working in the KDE version of the velocity field, right? So if you do the exact regression of the okay, so one idealization that I'm going to do is that I'm going to assume that the regression here is exact, so that each time you're basically solving the regression problem fully, and then like your update is exactly given by this particle recursion here, right? So in this idealized setup, if you let the eta go to 0, you will have this interacting particle system of in continuous time, essentially, right? So basically now the xi with a capital X corresponds to the continuous time particle system here, right? So this is the theoretical setup that we are going to be focusing on for the this is the setup we are going to be focusing on for the rest of the theoretical analysis of the talk. Yeah.
The xik are initialized how? The xik is initialized how?
The xik is initialized. So you're going to have a psi I, which is going to be some Gaussians, let's say, and then
With the initial model.
yeah, that is the initial model that's going to be give you the xik. Yeah, exactly. So now let's come to the point of how to define this velocity field, right? So what is the goal that we want to have for the velocity field? So it has to take in two distributions, and it has to be or some norm about this velocity field has to be 0 if and only if the two distributions are equal, right? So that's when your drifting next step will never get updated. You just get to a stationary point so that you don't move after the velocity field is like kind of like comparing the two distributions and telling they are the same, right? So that's the idea. And the original choice of the drifting field was based on like a normalized mean shift type of like a velocity field. So this m here for any density or any any density alpha. So you take a kernel k with some bandwidth h, and then you consider the mean with respect to the kernel of that bandwidth, of that density alpha, and then you normalize it with respect to just the density of the kernel essentially, right? So this is just a normalization factor here, right? So now what you do is like given the data measure nu and then your current particles density mu, you define your velocity field as just the difference between these two things, right? So this is the original choice of velocity field proposed by Deng et al. In their paper, right? So the intuition here is that the data term attracts so that like all the particles will try to get closer to each other, whereas the model term will ripple so that it will not also collapse at the same point, right? And again, now if people here are familiar with like Stein variational gradient descent, this is kind of like the same philosophy used in the design of SVGD for sampling as well, right? Except that the velocity field here is not necessarily a conservative velocity field. So meaning that it cannot be represented as a gradient field in some sense, right? So as an alternative, immediately almost after the original paper was proposed, several authors proposed this following alternative velocity field. So for any given measure or density alpha, you define the kernel-smoothed density as this k convolved with alpha, and then you just take the score of rho, right? So this is what was proposed as the so based on that, you just take the difference of the score with respect to nu and then the score with respect to mu, right? So this is what was proposed as another choice for this velocity field. And by definition, this is a conservative velocity field because it can be written as a gradient of a velocity field. Yeah. Sorry, a function. Yeah.
I couldn't understand why we need to keep it conservative.
Good question. So it's coming in 2 slides, as you can see. Right? So the question is like, so far what you have done is like, so the original proposal by Deng et al. Is like a conservative choice. The velocity field was non-conservative, and then many others have also proposed this conservative velocity field. Okay, so which one to use, right? So essentially, which is meaningful from practice, which is meaningful from theory, right? So the question is that before going to that, one advantage of using a conservative velocity field, as I was just alluding to, was like you can interpret the whole whole interacting particle system as kind of like a discretization of the Wasserstein gradient flow, right? So if you have the standard continuity equation of this Wasserstein gradient flow with this Vc, which is the conservative velocity field proposed here, you can basically think of the phi as like a scalar potential, and think of the velocity field as the gradient of the scalar potential. So you can think of the whole drifting as like a Wasserstein, from a Wasserstein gradient flow perspective. Is there a question or yeah?
So do also we need to make sure that this field is gradient of a convex function or some convex?
Yeah, so that's like a whole other thing, right? So then by OT, then it goes into the OT territory, right? So simple naive velocity field is you can also have the OT map minus x itself, right? So that is going to give you like a velocity field as well, except as long as you're able to estimate the OT velocity field directly, then you can just plug that into drifting and use that. I mean, that's basically OT itself, right? So it's also has its own connection. And basically, even this conservative and non-conservative velocity field there have been like some connections to like synchron regularization and things like that. So that's the whole literature. I'll not touch upon that. Right. All right. So why conservativeness matters? So basically, the whole philosophy of drifting itself was motivated as finding the stationary solution of a particular velocity field, even in the original paper, right? Now, if you're talking about like stationarity, it has to have a meaning, and the meaning is that like once you achieve stationarity, it has to correspond to something, right? So that notion of like stationarity corresponding to like a real stationary point where you no longer move makes sense only when you have a conservative velocity field, right? Otherwise, the curl in the velocity field is going to make you rotate even when you're inside like a neighborhood, so that like although you may be sort of macroscopically somewhat conservative, inside you may still be moving, right? So, and this is very clear in an example. So basically, here I have plotted like some example paths when you pass this point through conservative and pass a point through conservative and non-conservative velocity fields. So for the sake of like this simulation, I'm just illustrating only 4 trajectories, but then of course it is an interacting particle system that I use to simulate these trajectories. It's just visualization sake, I'm using 4, right? So you can see that like the solid red lines are basically from the conservative field, whereas the dashed line, the solid lines in all these 4 particles are from the conservative field, and the dashed lines corresponding to the respective non-conservative fields. So you can see that the non-conservative field actually has like some curvature, and that is basically from the curl in those velocity fields, right? So basically, this is like one motivation for like using conservative velocity fields from my perspective. Yes. Yes, they are very close to each other, but like, so you see here, like this goes away a little bit, and it may not settle down to the point. It may still just circle here, because if the curl is like more pronounced, it may get closer to the target and then just rotate there because it may have a non-zero curl. Right. Yeah.
Diffusion model don't have this conservative, right?
Well, so in the diffusion model, it is score based, right? So it's naturally conservative.
So in the optimal.
Yeah. Yeah.
But it's time dependent.
Yes, for each time it is a conservative field. Yes, I don't know if it's globally, and also in a sample setting, I'm not sure if it's proved as conservative. Yeah.
I mean, it's just a different problem. Diffusion model, you could parameterize energy, and the
Yeah,
score will be
yeah.
conservative, but that's not how it's done. So
That's
it's
not
not
how it's done.
conservative.
Yeah.
So but it's not a problem because you're a high dimension presume.
Well, I'm not advocating for one or the other.
I understand.
Just to be
But this
clear.
is a very different setting because you have
Yeah.
interacting particles.
Yeah. Yeah.
So then presumably conservativeness matters.
Matters more for sure. Yes. Yeah. All right. So now hopefully we are at some on the same page with respect to understanding about like what a drift model is. Let's look at like finite particle rates for this drifting models. So here is like exactly the full details written out. So basically, essentially, consider your x1 up to xn to be your particles, and you define your q as the KDE with the kernel k and bandwidth h. So for a particular point z, it's just the convolution of the kernel with the empirical measure of these points, let's say, and then you define the score of the q as like just the grad log of this thing, and then basically in the conservative setting, your rho is basically the the convolved so your nu is the target density, and your rho is your convolved. Take your target density and then convolve it to the kernel, right? So one thing to note here is that I do not make any assumption about whether nu is itself a density or it's just an empirical measure based on your target point cloud, right? So in any case, your rho is going to be a density because it's like a KDE convolution, right? So now your S rho is essentially going to be the difference between these two scores. And your interacting particle ODE is given by this equation right here. So now what first is the theoretical question should we ask here, right? You have this measure called as this Vn, which is just the average size of each of the velocity, conservative velocity field evaluated at each particle. The one thing to track is like track this Vn quantity over time, right? And if Vn is 0, then basically it is telling you that you're at an ideal stationary point, right? So one more drifting step at that stage would not change anything. Also Vn is by design designed to distinguish the data distribution and the current particle distribution. So if it is 0, it means that you're already generating data from the current the target distribution. So you're doing your intended job in some sense, right? So now in this finite particle setting, can you prove that this quantity over the time, so my particle setting is finite, my time horizon is continuous, right? So can you show that like this quantity becomes 0 during or decreases during training, right? So that's our goal here. And in particular, if you want to bound the Wasserstein distance, for example, between the current trajectory and the current empirical measure and after one step of this conservative drift step, where you have this mu tilde to be the empirical measure after one step. So you can bound the Wasserstein distance with the identity coupling as a root eta times this root of Vn as well. So essentially you're telling like even in a Wasserstein sense, the distribution won't move, right? So after this one step, right? So before we present the result, so I'm going to start by introducing the assumptions. So initially, the first assumption is like just some regularity assumptions on the kernel and the target itself. So I'm just going to assume the rho itself, the smoothed rho itself is like over the entire domain, positive over the entire domain, and then like the score is sufficiently smooth. It's not most important, but I'm going to be making two assumptions which really control what we can get for the rates and things like that, right? So the first assumption is something called as the reciprocal KDE control. So if you look at the velocity field's definition, there's like a score which is going to give you like a KDE in the denominator, right? So the sum of the inverse KDE at every point, the average of the inverse KDE, the KDE evaluated at each of the points. So we need to have over the entire trajectory range to be of some finite order, delta t, lambda t, right? So this is an assumption which essentially is trying to tell the KDE essentially remains sufficiently large at every particle location, right? So basically, so that the score and the interaction term do not really blow up, essentially, right? So the particles are also not getting isolated in the field, right? And then we also are going to make some smoothness assumptions on the velocity field itself. So for any function f, you can define the Stein operator of that function as the following. So for a function f, the divergence of f plus the grad log rho dot f is the standard well-known Stein operator. So uniformly over time and space, we are going to assume that the second derivative of the Stein operator is bounded by some function of h, and the second derivative of the velocity field itself is going to be bounded by some other constant, which is also a function of h, right? So the assumptions here are a little bit abstract. I'm going to demonstrate a few like illustrative examples with it. But intuitively speaking, what they mean is that essentially the drift field should not oscillate too rapidly inside like a size of neighborhood h, right? And essentially the best case regime for this assumption in particular is that when all the 4 derivatives of the score of the rho and the score of the KDE along the trajectory, they are all bounded by a uniform constant c, right? So if this happens, then essentially these two constants, the sum of these two constants is basically order 1. So one can prove that this will be the case. So now if you are giving me a Gaussian target and a Gaussian kernel, can you show that this assumption is satisfied? So it turns out that you can't show, I mean, this is not satisfied for the particular Gaussian target, Gaussian kernel case that I said just now. But there are some other examples where, like, if you have empirical measure targets and student T type of kernel, you can probably show that like this assumption is satisfied, right? So this is the best case scenario for our assumption. And then the worst case scenario, or not the worst case, but the not so good case scenario is basically like if the difference in the scores vary at some scale of h to the alpha, where alpha is between 0 to half, then essentially these two constants, the sum of them scale as h to the minus 4 alpha. So yeah.
Just want to understand your assumptions. So
Yeah.
basically we know KD is about a Finite-particles.
Yes.
So where does it show up in the assumptions?
So it will not show up in the assumption, it will show up in the rate. The usual curse of dimensionality will show up in the rates. And that, yeah.
So the assumptions that the fact that it's
Yeah. And in some sense, like even diffusion model behind the scene is a KDE, and the same curse of dimensionality shows up in like many estimation error rates for the KDE as well, like score estimation and things like that. So yeah.
Why do you say diffusion models are KDE?
Well, you have a KDE interpret.
Network, right?
The score estimation part of the diffusion model, if you bound the estimation error in a non-parametric way, that will also suffer from. Well, I can also do the same thing here and get improved rates then. I'm just making the most general assumption I need here. Right? Yeah. So essentially, because the whole point is like, in reality, you don't know which parametric model your data is coming from, so you want to be non-parametric, right? Anyway, you can take this discussion offline. Yeah. Anyway, so our first result, or the main result, is that the integrated the velocity field, the Vn quantity that I described here, the integrated Vn quantity has this rate. So essentially, it's like the KL. Oh, so I think maybe one thing I missed. Oh, so okay. I think I missed to say one thing. So this Hn of 0 is basically the KL divergence at the initialization between your particles and the n-fold product measure of the target. But I'll introduce that in a little bit. So that over nt plus some other constants over n, and then like half of this constants that I discussed previously times this m2, where m2 is just like the second moment of the kernel in some sense, and alpha h is like just this max of the Laplacian of the kernel and 0, right? So essentially the first two terms in the right-hand side correspond to the initialization, the finite particle interaction error, and then the last term kind of corresponds to the quadrature price, which we had to invoke in our assumption, right? So what we get from this result is that so at any random time you can basically bound the expected Vn, which is going to be like exactly equal to this integration, the error that we dealt with. So you can say that when this quantity will be less than epsilon, right? So it's basically like a random iterate guarantee, not a final iterate guarantee, right? So now if you're talking about like a kernel of this order, this structure, then one can show that AH, the constant is of h to the negative d minus 2, and then the MH, the second moment is like of the order of h squared. So as we told, like the sum of these two constants is like some h to the negative beta for beta less than 0 to 2. So if you put everything together, your bound will be of this order here, and then if you balance the h star, the optimal h star is like of this order, and essentially if you put this h star back into this bound, you're going to have this n to the negative something which has this curse of dimensionality which we usually see in. The only difference is that it's not a single static KDE estimator, it's like a interacting particle system based KDE estimator, so you still have to deal with the interaction term here. That's the key. Yeah.
So we have this interacting particle that
Yeah.
depends on each other, right?
Yeah.
So they are both dependent, their location are dependent.
Yeah.
So in the diffusion model, you have basically one particle whose distribution. Basically, I think, so my question is that this interdependency between particles,
Yeah.
does it create a
Yes.
problem for sampling?
So that's the whole difficulty in handling the proof in some sense. And the way to deal with that is like through something called as propagation of chaos. So essentially one can show that like if you initialize IID, if you have some nice properties, then it will kind of, you can basically treat individual particle as like independent items, and then you can just reason about like individual particles, essentially not worrying about this dependence that you are talking about. So that's how the proofs roughly proceed, right? And coming back to the best case scenario, when beta is 0, you get a slightly better rate compared to what we have here, which is like negative n to the negative 1 over d plus 4, which is still has this curse of dimensionality here. So now I'm just how much time do I have? Like maybe 5 minutes, maybe. Yeah. Okay. So in the time that I have left, I'm just going to give a brief idea about the proof. So I just want to say again where I started with. So this whole story or analogy between like SVGD and diffusion or Langevin, Monte Carlo and things like that is kind of like repeating after like 10 years now with like diffusion models and drifting models. So naturally, over the last decade or so, so we have been looking at understanding first the sampling version, which is the SVGD problem itself. So only recently we have been able to get like finite particle rates for the SVGD problem, and you can. This is in collaboration with various authors, including Sayan Banerjee and Anna Korba and. Also, Ye, who is here, is an author in the regular SVGD paper. So, and in particular, our recent result is telling like a uniform in time, you have a propagation of chaos. So basically, like you can treat the individual particles as independently evolving. So that's the latest result we have on SVGD. So all of the proof structure that I'm going to, all of our proofs for the drifting itself is motivated by the proof structure of SVGD, right? So. Like what happened in diffusions, basically a lot of the Langevin Monte Carlo people had the machinery to understand like non-asymptotic guarantees for Langevin Monte Carlo. They were able to translate those ideas to the diffusion models and get like sampling error bounds for diffusion models. So the same analogy is happening here, which is like all the rates which we can have for the recent rates for SVGD which we are able to develop, now we will be able to drift it to drifting model itself, right? So essentially, the main idea behind the proof is that instead of looking at the empirical measure of the particles and the target density, the right object to look at is like the KL divergence between the joint density of the n particles and the n-fold product measure. And the reason why we can have this n-fold product measure as comparison is that because of this propagation of chaos, the joint density is actually like independently evolving. So you can directly compare to this n-fold product measure. So that's the key idea which enabled us to get the rates for SVGD. based on that, so you can just take the derivative of this KL of the joint particle, and then you can get like a term like this. So if you do not have this second term here, then this is exactly like a gradient flow equation. So you will be able to get like a clean result. But what we will be able to show is that like this term here will be like of smaller order as well. So even with an additional term here, whatever you can show for like just a regular gradient descent analysis, it goes through with this additional residual term. So that's exactly what we showed. So essentially the first result we have is like for a quantity which is like giving you the gradient structure, you have a upper bound which gives you the first two terms. And then the second observation is that like what we wanted to bound was this quantity, but the thing that we bound in the previous step is not really this quantity. So essentially we can show that like there is a connection between like you can control the distance between like the quantity we are able to bound and then this Fisher discrepancy, which is defined as the expected version of your Vn in some sense, and then the Vn and In itself are bounded together, are bounded by this quantity. So these essentially give you the third term in the upper bound that I showed previously, right? And in the interest of time, I'll skip the. So if you remember in the first assumption, there was this reciprocal KDE control. There are some conditions under which we can show that the reciprocal KDE control probably happens as well, but in the interest of time, I'm going to skip that. And probably the last part of the talk was essentially the same type of results for non-conservative drifting fields, which was the originally proposed version of drifting fields in Deng et al.'s paper. Obviously, it doesn't have a gradient flow structure. So the main idea is in this slide. So in a related paper by Franz et al., they kind of propose this idea of like a sharp companion-kernel decomposition where your non-conservative velocity field could be written in this particular form where you have a conservative velocity field and then you multiply that with some other coefficient and then have some residual error, right? So in many cases they showed that like this non-conservative velocity field could be written in this affine transformation type of a conservative velocity field. So we use that to essentially make an assumption on how much mismatch is there between this the error and the conservative velocity field. So essentially, so without going into much of the details, so you have the same type of bound for this case, except that there will be an additional term here, delta H, so which is never controlled by the number of particles here. So in the previous case, the number of particles will control all the terms on the right-hand side, but this will be a negligible or non-negligible residual error, which was the reason why in the initial parts of the talk I was telling like you get closer to the stationarity, but you will never be exactly zero because there will always be this non-negligible term because your velocity field is not really conservative in that case, right? All right, so essentially in this talk, so we discussed about like what one-step generation with drifting corresponds to and how it kind of is modeled as an interacting particle system. And then we presented like results for two types of velocity fields used in drifting. One is a conservative velocity field where you have this connection to Wasserstein gradient flows and everything. And then the other is the non-conservative case, which was the original proposed velocity field. There's a lot of questions to be answered here. So what other theoretical questions to ask is the first question in some sense. Yeah, so with that, I'll end my talk and happy to take questions. Yeah.
So why don't people use much simpler thing like you match the initial particle to the target particles and then do linear interpolations?
I think that's like the flow matching, right?
No, you match them and then you learn the model. If I understand correctly, this particle motion is just to update your model, right?
Yes, yeah. So you match you just randomly match the particles.
You do them.
Yeah.
Max weight, min
Yeah,
weight
yeah. So
matching.
that is basically connected to flow matching, right? So you just connect the particles, and connect the initial particle and the target particles, and then just learn the velocity field that maps these two, right?
Well, you don't. You learn just one step. I'm proposing to learn it one step.
So how to do that in one step?
Okay, perhaps we can take it online.
Yeah.
But if I understand correctly, this velocity field is just, again, to have a sequence of problems that
Exactly.
you learn.
Yeah. So one thing I can say, at least from empirical perspective, I think, as also was alluded in the previous talk, it seems like people started with diffusion model. So they still want to have some gradient-based system to learn something with gradient descent, or preferably a neural network with gradient descent. But at the same time, they also don't want to do that at inference time. So they want to do it at training time. So that's how it seems like they arrived at this logic. But an immediate, like a one-step generative, even OT map is a one-step generative modeling thing. So as long as you have OT map between two densities P and Q, or two particles P and Q, then that is already a one-step generative modeling. Somehow, like, people have not made it work as well as these methods, it looks like, in practice. Yeah.
So I have a question about, do you find it puzzling that, under the hood you're using this KDE and drifting model works on ImageNet?
Yeah.
And clearly I don't know what that KDE is doing there, because
So-
clearly it's a wrong estimator.
So two questions. So firstly, the main reason why drifting got attention is like they essentially worked in some feature space, and then they made this KDE-based estimator work for ImageNet.
I see.
So that is the real reason why drifting caught up with, like, people. It gathered attention with people.
So if you do it in actually pixel space, it just doesn't.
Yeah. So it's only in the latent space that's easy.
What about on CFAR? Does it work on CFAR in pixels?
I'm not very sure which data sets they use. Maybe, I think, but Yulin Du has to be here in the next few days, so you can also ask him directly. How did they make it work? But that was the reason why it got attention in particular.
Every question that you answer sounds fisher.
Yeah. But coming back to the point, even like the score estimation, it is if you want to do it non-parametrically, it is a non-parametric.
The score estimation is related to a denoiser, right? And
So-
the denoiser is done with a big neural net. It's not a KD. I disagree with you, but we can
Yeah,
tell offline.
I can explain it offline. So there is an interpretation which you can have as KD. Yeah.